Thank you very much for being here today. And well, first of all, I really would like to thank the organizers for having put together such a beautiful meeting. So I typically work, I'm a theoretical physicist, but I typically work within quantum information theory. And so today, because I think I will be talking to a slightly different community from the one that I'm usually talking to in conferences, I will focus more on concepts rather than technical details. So just to break the ice, because it's a long time that I'm not giving presentations in front of a real public. Did you recognize this one? This is just hanging there at the coffee room. Because I found it because I was looking for some proof of connections between Satoshi Watanabe and Yukawa. So Satoshi Watanabe is also a famous Japanese theoretical physicist, and he's basically contemporary with Yukawa. Yukawa was born 1907 and Watanabe in 1910. And so I was sure that they would know each other because also Yukawa was working on particle physics and like Yukawa. So I was looking around for some connections between the two, and I found this one. So this is the present that Watanabe gave to Yukawa in the 50s, I think, when they met for some conference. And then I wanted to understand what this is about, because I'm sure that two theoretical physicists of that rank, they cannot exchange just plain and boring presents. For sure, there was a meaning behind this present, right? So I searched about what this is about, and so this is a story called like The Happy Fish, and it's an excerpt from an old Chinese poem or novel, and two people are walking along a river, and one guy tells to the other, "Oh, look, the fish, how happy they look like." And the other guy says, "How do you know that the fish is happy? You're not a fish." And so they keep on discussing about these things. And basically, the moral of this discussion is that observation, I mean, reality, what is around us is always observer dependent, right? So we put our beliefs in what we see, and we can see, for example, a happy fish, even though we are not fish, and fish are not able to tell us whether they're happy or not. So this is going to be about the role of observer in the definition of entropy. So there are going to be basically three characters here: an entropy, and then a paradox that makes the interpretation of the entropy difficult, and then somehow the paradox can be resolved if we are ready to add an observer in the picture. So the ideas that I'm going to tell you about today stem from discussions with some collaborators of mine, Clive and Valerio, which are both based in the Center for Quantum Technology in Singapore, and Dominic Shafranek, which is based in IBS in Korea, and Joe Schindler, which is now based in Barcelona in Andreas Winter's group as a postdoc. And a few days ago, Dom prepared this homepage, the Observational Entropy Appreciation Club. By now, the members are me, Dom, Joe, von Neumann, and Wigner. So, if you want to be part of such a club, you're happy to join. Okay, so the first character we are going to talk about today is von Neumann's entropy. Okay, so we've seen this quantity appearing very often in the talks that we've listened to in these days. Yesterday, Hoji gave a very nice talk about, based essentially on the notion of von Neumann entropy and derived quantities like coherent informations and so on. So this is a fundamental quantity, and we use it a lot. But unfortunately, there is a problem with it when we try to apply it to thermodynamic situations. And this was noted by von Neumann himself. He writes this in a paper in which he proves an H theorem, which has been translated relatively recently by Tumulka, and the translation is available on the archive at this number. So von Neumann writes the following. The expressions for entropy given by the author previously, the author is von Neumann, of course, are not applicable here in the way they were intended, as they were computed from the perspective of an observer who can carry out all measurements that are possible in principle, that is regardless of whether they are macroscopic or not. So what it means by this, what does it mean that von Neumann entropy somehow is an optimal quantity? So if you turn this into a mathematical formula, you have this theorem. So it is possible to prove, it is not difficult to prove actually, that given a density matrix rho and some orthonormal basis phi I, and defining these numbers, this pi, as the probabilities that you get by projecting rho onto this orthonormal basis, von Neumann entropy can be written, can be represented as the minimum entropy of these quantities that you can measure, taken over all possible orthonormal bases. So it means that von Neumann entropy somehow measures a minimum amount of uncertainty that is associated with some density matrix. This is what von Neumann meant in the sentence that we've seen before when he was writing that von Neumann entropy, well, he wouldn't call von Neumann entropy, but he would say the entropy that the author introduced previously quantifies the information, the belief, the knowledge that like a almighty observer might have about the quantum state rho. And now von Neumann presents a paradox with this. So he essentially argues why von Neumann entropy is lacking some aspect in order to describe thermodynamic situations. So this is an excerpt from von Neumann's book. So the book about the mathematical foundations of quantum mechanics that was published just a few years after, 1932. And this is taken from the translation in English dated 1955. So although our entropy expression, as we saw, is completely analogous to the classical entropy, it is still surprising that it is invariant in the normal, and I would explain here that he's speaking about the Hamiltonian, okay, the closed system evolution in time of the system, and only increases with measurements. Instead, in the classical theory, where the measurements in general played no role, it increased as a rule even with the ordinary mechanical evolution in time of the system. It is therefore necessary to clear up this apparently paradoxical situation. So the situation that von Neumann has in mind when he speaks about it is the free expansion of an ideal gas. So you start with a container made up of two volumes of the same size on the left and on the right, a container that is adiabatic. It is adiabatically isolated from the environment. So there is no exchange of heat, okay? And at the beginning, all the gas, ideal gas, okay? All the gas is constrained to be in this left half of the container. Then we open the valve, and the gas is left to expand freely in the other chamber where the vacuum was prepared. So the gas expands without doing any work. There is no heat exchange because the walls of the container are adiabatic, and therefore the temperature doesn't change. The temperature is a function of the internal energy, or well, the internal energy of the gas is a function only of the temperature, which does not change, but the pressure becomes half at the volume twice. And if you try to compute the change in entropy that this evolution causes in the whole universe, it's strictly positive. So this is free evolution because, you know, the system is just freely to evolve with the other half. We are just changing basically the Hamiltonian, the geometrical constraints of the piston. But I mean, this is just left expanding unitarily, Hamiltonian, according to Hamiltonian mechanics. However, the change in entropy in the whole universe is strictly positive. And this can be, can be proved in different ways. The easiest way to prove it is to try to close the cycle and to bring the gas back here, and you can do it with an isothermal semi-static compression process, and this would give you exactly the heat transfer needed to bring back the gas on the left side. So we are facing some paradox that is not so different from, I would say, the black hole information paradox, right? So also here there is something that physics would say it's a unitary evolution, so in a reversible evolution, but microscopically speaking, but the entropy production is strictly positive. And so the problem that von Neumann finds in this is that instead, as we all well know, for any unitary operator, von Neumann entropy does not change, simply because von Neumann entropy is a function only of the eigenvalues of a density matrix, and these are invariant under unitary transformation. And this is how von Neumann understands this paradox, solves this paradox. And of course, he's inspired by previous work by Szilard. So he says, he writes in the same book, after presenting the paradox, he writes, of course, for a classical observer who knows all coordinates and momenta, the entropy is constant, right? So if we could follow the trajectory of each single particle making up the bulk of the ideal gas, there would not be any entropy change. So the time variations of the entropy are based on the fact that the observer does not know everything. That is to say that he cannot find out, measure everything which is measurable in principle. So the increase of thermodynamic entropy in a free expansion is due to the fact that the observer has limited capabilities. Okay? So that we really, in order to understand what's going on there, we really have to put the observer there with an active role in looking at the thermodynamic system as it evolves in time. Okay, so how can we put the observer in a formal way, in a mathematical way, inside the equation of the entropy? So this is von Neumann's proposal. So after that discussion of the free expansion paradox, he goes on and introduces a quantity that he calls the macroscopic entropy, to distinguish it from the other quantity that he defines, which is now known as the von Neumann entropy, which he regarded as a kind of microscopic form, or the entropy corresponding to an almighty observer. Okay? Instead, this is a macroscopic entropy, which is related to a macroscopic observer that has some limitations in what they can measure. So the definition requires a density matrix rho, a set of orthogonal projections that resolve the identity, and then you have these numbers pi, which are the trace of rho with pi I, and these terms that are considered the volume terms that are the trace of these projectors. Okay? So putting these numbers together, he proposes this formula. So this is the macroscopic entropy of rho with respect to projectors P, and it is defined in this way. So it is not just the entropy of these probabilities Pi, but you see that there is going here, there is this volume term that divides the entropy. So this object here is interesting, right? Because it seems to be a kind of interpolation between Gibbs entropy, which would be when these omega I are all one, okay? And also Boltzmann entropy, which would happen, for example, when these omega I instead are much, 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 much larger than one. Okay, so these omega I, which are the rank of these projectors, okay, or the dimension of the subspecies of this projector, can be understood as somehow these macroscopic cells into which the phase space is divided. So in particular, for today's talk, we will consider a modern generalization of this von Neumann's macroscopic entropy, which goes under the name of observational entropy. So in order to introduce observational entropy, again, you need a density matrix. And now the set of projectors is replaced by a positive operator valued measure. So these are positive semi-definite operators that sum up to identity. And this is very important to have because typically a measurement that you perform in the laboratory does not correspond to an orthogonal set of projectors, but it corresponds to a POVM. And then the rest is the same. So the PI are the probabilities of obtaining outcome I on state rho, and these VI are the traces of the elements PI. And this is the definition of observational entropy. So you see that also notationally now, there is another symbol here, P, that determines the POVM with respect to which this quantity is computed. And well, it was introduced in these two papers here by Dominik and collaborators. So observational because it is the entropy of the observer, is the entropy with respect to the observer. Why? Because von Neumann defines a macro observer as a collection of simultaneously measurable quantities, Q1, Q2, Qn, and so on, where these things are all, well, for von Neumann, these were all observables, but now we can understand this as being all POVMs. So a macroscopic observer is mathematically modeled as a set of measurements that can be done simultaneously.
Just a small question. When you had introduced earlier von Neumann's definition and then this generalization for each fixed either projection valued measure or positive operator valued measure, I'm a little bit surprised that there's no minimization occurring here, like in the previous definition where you maybe fix like the dimensionality. Let's say like you have a macroscopic observer who only has access to certain like a certain resolution.
The dimensionality here is fixed by the state.
Oh, I mean the dimensionality of the orthogonal resolution, because in the previous setting where we were looking at ordinary entropy, the dimensionality was always one.
Yes.
So I'm curious if there's like a minimization procedure that you can
No, this is fixed. So you give me an orthogonal resolution of the identity, and I write down this number.
Okay. Okay, thank you.
Welcome. Okay, so now, you know, according to recent results in quantum measurement theory, we know that if you have a family of POVMs that are simultaneously measurable, it means actually it's equivalent to say that there exists one mother POVM and stochastic processings, mu, such that essentially just by measuring this mother POVM, we are able to reconstruct all these simultaneously measurable quantities just by means of a stochastic process, post-processing of data, okay? So for von Neumann, the POVM corresponds mathematically to the definition of a certain macro observer, okay? So that's why observational means observer, and the observer becomes just this P. Okay, so we are not speaking about mind or, you know, relation between mind and matter or whatever. No, mathematically, this is just a POVMP that it is used in order to define the observational entropy. Okay, so now I would like to discuss with you some of the mathematical properties of these quantities, because these are extremely interesting, and not only interesting mathematically, but also, and in particular, I would say interpretationally relevant. Okay, in order to study the mathematical properties of observational entropy, we start, as always in these situations, from Umegaki's relative entropy. Okay, so it is this quantity, and I think you've seen it very often. And it satisfies some basic fundamental properties that are extremely useful when you do proofs. So the first one is when you have two states, A and B, this quantity is always greater or equal than 0. And then from here, you can actually compute von Neumann entropy of rho in this way. So this can be thought of as a kind of parent quantity for von Neumann entropy, where U, this second state here that appears on the right, as the maximally mixed state. Is the state corresponding to a uniform distribution of outcomes, of eigenvalues, actually. Here, there is no outcome yet, right? I'm not doing any measurement. And then, like, crucially, Umegaki relative entropy satisfies a monotonicity property in the sense that whenever we apply on both rho and sigma the same channel, which in the language of quantum information theory means a completely positive trace-preserving linear map, this Umegaki relative entropy decreases. Okay, it will never increase. So it's a kind of divergence, and actually in the statistical literature is called the quantum divergence quantity, that by applying some noise, you know, these two states cannot become more statistically distinguishable than they were before applying the noisy map. So this will be crucial here. And just by using monotonicity of Umegaki relative entropy, you were already able to prove a bound on observational entropy. Okay, even though this was defined as a minimum, but it was a minimum on rank 1 POVM. So, you know, this is something a little bit more, that for any state rho and any POVM PI, the observational entropy is lower bounded by conventional von Neumann entropy. And the proof is very simple, but it is important because it gives us a very nice, a very useful, I would say, representation for observational entropy. So the proof is just a few lines, so we can just go through it together. So given a POVM, we define the following channel as this. So you see that I am measuring POVM PI on the input state, and then I'm just putting the output probability distribution of outcomes on the diagonal entries of some other state. So it is a way basically to say that I'm encoding this information about outcome statistical distribution on a kind of classical states. So these I's are all orthogonal to each other. And then using this CPTP map P, it is possible to write the difference between observational entropy and von Neumann entropy in this way. So you see that we have a difference between Umegaki relative entropy between rho and u, and Umegaki relative entropy between rho and u after the measurement map P has been applied on both. So this is a channel, and therefore this difference is non-negative due to the monotonicity property we've just seen before. But now, because we were able to write the difference of these two as a difference of two Umegaki relative entropy, we can use one of the most insightful, I would say, results in quantum statistics, which is a famous theorem by Petz that essentially aims at sharpening our intuition into this inequality. So in general, we have this. So Petz in the 80s asked this question. So for which triples, rho, sigma, and channel E, we have that these two quantities actually coincide? So for which triples we don't have any decrease of Umegaki relative entropy? And Petz famously answered this problem in this way. So this happens if, and only if, the transpose channel, which is this thing here. So you see that it depends on the original channel E, but it also depends on the state that we have on the right of the Umegaki relative entropy, the sigma. And it is constructed in this way. Here is your input. And here you make this sandwich with the inverse of the square root of E of sigma. Then you apply this E daga, which is the trace dual or the Heisenberg picture version of your channel E. And then you sandwich with the square root of sigma. So this is true. This equality holds if and only if taking the output corresponding to rho through this transpose channel gives you rho again. And of course, the other equality also is satisfied, but this is satisfied by construction. So it's not interesting. What is interesting is this thing here, that this map that does not depend on rho, but depends on E crucially via sigma, is also able to bring you back to rho. And this is the famous Petz recovery map or Petz transpose map that is appearing in so many areas of physics, and we will see why. It appears in quantum error correction, it appears in quantum fluctuation or fluctuation theorems. It appears in black hole thermodynamics and black hole physics. But why? Why is it so crucial? And one thing to keep in mind is that this Petz transpose map in general is not the linear inverse of V. It's a completely different thing. It has to do instead with statistical retrodiction, not with linear inverse. Okay, so what are the consequences of Petz recovery theorem on observational entropy? The consequence is the following, that observational entropy coincides with von Neumann entropy of rho if and only if rho can be decomposed in this way. So here you have the probabilities that rho induces via the measurement pi, and here you have this normalized POVM elements, which now therefore are density matrices, right? Because pi is a semi-definite positive operator, and we are just dividing it by its trace. So this guy here is a density matrix, and we're taking the convex combination of these density matrices with the probabilities that rho induces via pi. So if rho satisfies this equality, this recursive equality, this recursive equation, then we know that the observational entropy is equal to von Neumann entropy. And the proof is again 3 lines given Petz theorem, because if you construct, you remember that we could write the difference of these two things as a difference of 2 Megachy entropies. So these two things are the same if and only if this map, which is the Petz transpose map of this measurement map P, brings rho back to itself. And by direct inspection, you can see that this guy is exactly this thing here. So, a question that one might ask is, because this equation is defined recursively, do you have at least one rho that satisfies that? Well, yes, typically at least one. You always have at least one rho, and of course, that rho would be the uniform distribution, right? For any POVMP, at least one density matrix rho exists such that its von Neumann entropy is equal to the observational entropy. For example, the uniform, but there might be more. Okay, it really depends essentially on the subspace of fixed points of this CPTP linear map here. Okay. So how observational entropy resolves the paradox of invariance of von Neumann entropy under free evolution? Okay, so let us start at time t equal to 0 from a state of maximum knowledge. So suppose that at time t0, the observational entropy coincides with von Neumann entropy. And now suppose that the system undergoes a unitary evolution that brings it from time t0 to time t1. Then what you have? So let's try to compute the observational entropy at time t1. So this will be the definition of observational entropy. You see that I'm taking the evolved state here and here, but the POVM is the same, right? So this is exactly the definition of observational entropy. But using the cyclicity property of trace, I can bring these unitary operators on the POVM, and I can just, insert here some identity. So I can also change this guy here at the denominator. But what is it now? So this is the observational entropy of the state at time t0 through a Heisenberg propagated POVM, U daga PU. So putting these things together, what we have? We have that the observational entropy of the state rho at time t1, which is equal to the observational entropy of the state at time t0 through the Heisenberg propagated POVM, is going to be greater or equal than the von Neumann entropy at time t0, just because this need not be the optimal POVM anymore. And this is equal to the observational entropy of rho at time t0. So looking only at the initial point, at the final point, we have that the observational entropy of rho might increase even under a unitary evolution. So when does it not? It does not increase, so it remains equal only if, because now we can use again Petz recovery theorem, only if this equality holds, that is, I will try to write it again in a more understandable form, only if this holds, that the state at time t0, which was written as this, under the unitary evolution becomes this thing. So you see that essentially structurally, the state does not change. It is always a convex combination of these guys. It is only these numbers that might change, but they might change in a way that the entropy remains the same. Okay. So essentially, the state is structurally invariant. Only in that situation, observational entropy remains the same. So in other words, even if the evolution of the system is unitary, if the P of M, or if the initial state does not satisfy some stronger structural invariant, some properties that remain invariant under this unitary evolution, the entropy, the observational entropy will increase. Okay? So observational entropy generically increases, even if the evolution is unitary. Okay, now another question that it's interesting to ask from the mathematical viewpoint is the meaning of a finite difference here. So what is the meaning? What can we say if these things are not the same, but if this difference is strictly greater than 0? So in this case, we have this elegant formula, elegant bound for this. So for any density matrix rho and any P of MP, this difference that, you know, might be 0, but might be also positive, in any case, always upper bounds the Omega-K relative entropy between your initial state rho and this guy rho CG, CG because coarse-grained, which is defined by this formula. So you take your measurement map P and you apply P tilde U on rho, and this is the coarse-grained version of rho made through the lenses of measurement P. So this rho CG is the coarse-grained state inferred from the measurements data. Why? Because an interesting thing is that notice that this guy rho CG is completely determined by information that is in the hand of the observer, because it depends on the measurement and it depends on the measurement outcome statistics. Okay. Whereas rho might not be directly accessible to the observer. Rho is some kind of microscopic underlined thing that causes the stochasticity of outcomes. But rho CG instead is the state that can be inferred from the measurements data. And this is the coarse-grained state, it's called CG. So what is stronger than a strong bound? An equality. And indeed, the bound that I showed you before can, well, if you follow the same bound along a different direction, you reach an equality for observational entropy, which is as follows. So now this is, for me, this is the most interesting part of the presentation. And also, this will bring us back to Satoshi Watanabe painting outside in the coffee lounge. So the theorem is as follows. So given a d-dimensional system, a density matrix rho that is diagonalized in this way with eigenvalues lambda x, and the P of MP, now let us define two joint probability distributions. One, which is this forward probability distribution, where we essentially prepare these pure states phi x with probability lambda x, and then we measure them using the P of MPI. On the other side, we have this thing here, which is also a joint probability distribution on x and I, but is defined in this way. So now what we do is that with probability pi, hey, we prepare these states here, pi divided by vi. These are density matrices, and we now measure them on the basis that diagonalizes rho. So the rho of measurement and input state somehow is exchanged. But if these are two normalized probability distribution, and then the difference between observational entropy and phenomenon entropy is equal to the Kalbach-Leiber divergence between this PF and PR. exactly equal. It's not a bound, it's a equality. So you can picture this, the situations in this way. So on one side, we have that we're preparing these pure states phi x with probability lambda x and sending them through the measurement pi. In this way, we get this p forward. On the other case, we start from these density matrices pi divided by vi that we sample with probability distribution pi, and we send them backward. This arrow is not time, okay? This is not time. This is just a space arrow. So you can imagine that on one side you have things that depend on phi, and the other side you have things that depend on p, okay? But here you prepare these things and you measure them on this orthonormal basis phi x, and you get the reverse joint probability distribution. The Kullback-Leibler divergence between these two is equal to the difference between observational entropy and von Neumann entropy. So now the interpretation, and the interpretation is very nicely given in terms of prediction and retrodiction. So start from this forward probability distribution, okay? So this can be seen as some lambda x, which is the probability with which we prepare these pure states phi x, and then some conditional distribution. It's a kind of channel, okay? It's a kind of stochastic processing that given x outputs I in a stochastic fashion. So notice that if we take the marginals of this joint forward distribution, we get lambda x on one side if we sum over I, and on the other side, if we sum over x, instead we get the trace of rho pi. Okay, so these small pi's here. So if we want to write the situation with some arrows that make, maybe easier to capture what's going on here, you can say that you start with some input distribution lambda on the eigenvalues, okay? And then you propagate this through this stochastic processing pi, and the output that corresponds here is the probability distribution p, right? So I hope that this way of writing things is clear to everyone. So now let's take a look at the reverse probability. So also this guy here can be written as pi times some suitable conditional probability distribution now where the input is I, and for each given I, there is some kind of stochastic distribution on the x's. But what is it? So let's try to rewrite this conditional reverse. So this is the definition of it, right? So this is this part, and here I'm just rewriting the volume term. Okay? So this is the volume term because taking the sum over x of this is the trace of pi, right? So now I just add this dummy number here, which is dimension to the -1, both in the numerator and the denominator. And I just call it the uniform distribution. So just for the sake of notation, let me call it ux, even though actually this does not depend on x. But what is it? Now, if we write it in this way, what is it? Now, this is the forward probability distribution. And this is normalized by the marginal, right, on the I. So what we're doing, this is just Bayes' rule. This is just Bayes' rule. So this PR, which is the reverse process, is just the Bayesian inverse of the process pi done with respect to the uniform distribution U. Okay, so what is the interpretation of this situation? So this falls squarely into the theory of probability kinematics devised by Jeffreys in the 60s in order to understand belief propagation in networks and in logical reasoning and statistical inference. So in the language of Jeffreys probability kinematics, what we have? So we have on one side this forward joint probability that corresponds to the prediction. So this PF would be the probability that an agent that knows the probability on the input lambda and knows the channel pi would predict. So it's an inferential prediction about the measurement outcomes I. Okay, the measurement is not done yet. This is just a computation done on paper, and this is your prediction, the prediction that the agent knowing the initial conditions would do about the measurement outcomes. The other thing instead corresponds now to a retrodiction that starts instead from the measurement outcome P and back propagate this information onto the input letters here. So what is this? This is the inference about X. X is the input, okay? The state, the information about the quantum state, the eigenvalues, that a completely uninformed Bayesian agent. Why completely uninformed? Because you have the uniform distribution U here, would do if given information about I in the form of the probability distribution P. So you are sitting at the end of this channel, okay? So you're looking at the outcome statistic, the outcome probability distribution at the output of the channel, and you have absolutely no clue about the input. So you model the input as a uniform distribution. So the retrodiction that you would do in this situation corresponds exactly to this reverse process. And so what we see that the equality occurs if and only if predictor and retrodictor agree. So in other terms, you have an increase in observational entropy if and only if predictor and retrodictor do not agree. So if and only if predictions and retrodictions lead to different conclusions. And this is where we connect with Watanabe, because one of his main points of contention since his papers published in Physical Review in the 50s and then subsequent literature is this. This is in an abstract of a paper that he published in 1965, and he exactly writes the phenomenological one-wayness of temporal developments in physics is due to irretrodictability. He uses exactly the word retrodiction, irretrodictability, and not due to irreversibility. So there is no paradox with this reversible thing. It is just, you know, essentially what we have is that the second law of thermodynamics is not about the arrow of time, okay, but only about the arrow of inference. And you cannot really escape from here. The second law of thermodynamics, the increase of entropy is not a time. It is just an inferential arrow. And these are two papers in which we discuss this arrow of inference in relation to fluctuation theorems in statistical mechanics. Okay, so it's perfect. I just have 2 minutes and I can conclude. So take-home messages. Okay. When the use of von Neumann entropy in thermodynamics is problematic, and you know, I cannot help but thinking about the information paradox, but you are the experts about it. So try consider observational entropy instead, because why? Because von Neumann told you so. Well, no, it's just joking. So because OE has a fully operational inferential definition, and we like it, no? Because it's pointless to talk about physics if you cannot make experiments on it. Right? So it is important that a definition is entirely operational and inferential. It does not rely on some unobservable degrees of freedom. The definition of observational entropy essentially can be computed just by looking at the measurement apparatus and its outcomes. You don't need to know the input state. Then another good point is that observational entropy unifies Gibbs and Boltzmann entropy. So for people that were wondering, oh, there are these two entropies, they're slightly different, but I can use both, but which one? If you are in troubles, just use observational entropy because you get the best of both, okay? It's a way to unify them both. It solves interpretational paradoxes, right? So when you have things like unitary dynamics that lead to a net increase of entropy, or perhaps if you have unitary dynamics that leads to a net decrease of entropy, maybe, you know, because you'd better consider an observer in the picture. Also, another things that maybe is most tantalizing for those of you well-versed in algebra and mathematical statistics is that it fits very nicely within recent developments in quantum mathematical statistics, especially, you know, it seems to be, you know, defined on purpose to be analyzed using Petz recovery maps, which are all over the places as of lately. And then the fifth reason that for me is the nicest one, but of course this is open to discussion, is that this observational entropy has built in a concept of Bayesian prediction and retrodiction, because just the difference between observational entropy and von Neumann entropy is equal to the relative entropy between the predictor probability and the retrodictor probability. So it seems that we are, pushed towards the conclusion of trying to consider prediction and retrodiction in physics rather than a forward process and a reverse process. I don't like when people speak about time reverse process. To me, it doesn't make much sense because we can't inverse time anyway. You might construct a Hamiltonian that simulates Udaga, but what is Udaga? Udaga is the retrodiction thing of U. You don't bring time backwards. And that's the end. Thank you very much.
Thank you very much. Very nice talk. And
Thank you very much for interesting talk. I have a question about the time allow of time. So let's consider a low entropy state as the initial state. Okay, so classical evolution, quantum evolution, both is okay. But after time, the entropy becomes increased. But if we wait for very, very long time, order of the Planck time, then the thermal entropy should go down, should decrease it accidentally. Then such a phenomenon can be interpreted from viewpoint of your observational entropy. I have an interest in that. So can you explain the such a decrease of thermal entropy from viewpoint of observational entropy? Or
so there wouldn't be any decrease of entropy there, because you would be you would be an observer that knows something at the beginning, and then your knowledge just goes away. So it might be that entropy at some point in the future might, because for some statistical fluctuations, the particles of your ideal gas might be in a certain moment, they might go back on the left side, but you don't know that. You don't know what's that moment. So for you, nothing changes.
Sorry.
You don't know when this happens. So you don't know when these things go down that you can insert back the valve and go back to the initial situation. This will happen, but you don't know when. So for you, this has zero meaning.
You're right. So I cannot predict the time when such entropy goes back.
Yes.
But if I have a very long longevity, and if I can still alive, then I may know.
No, because you don't know when it happens. It will focus back for a certain moment, but then again expand.
Yeah, sure.
So then, you don't know when this happens. So you cannot do anything with it.
Okay, so you don't care about such an abrupt decrease of entropy.
Yes.
Because just the accidental and transient phenomenon.
And not measurable. That's the most important thing. That's not observable.
Wow.
You wouldn't be able to observe that because you wouldn't know where to do the observation.
If we consider any particle in a box, then so we are the outside of the world, then so particle can go to a very small entropy state.
No, how do you? Because you have to measure entropy. So measurement of entropy is a measurement of heat or measurement of temperature.
Oh,
right.
Okay, so please discuss later.
Yes, but very interesting point. But I am absolutely convinced that these fluctuations, these recursive theorems, and so on, play absolutely no role in the discussion of observational entropy. But very good point. I'm very happy to discuss more about it.
Okay, thank you. Then next question is here.
Yeah, thanks very much for the really nice talk. So I'm wondering whether you have any thoughts on other applications of this operational entropy, for instance, in the context of classical limits from quantum theory.
A lot has been done. So I'm not an expert, so I didn't talk about it. But my collaborators actually have been looking on observational entropy from the viewpoint of statistical mechanics. So actually, the original goal was to give a definition of entropy valid for systems out of equilibrium. And for example, there is a recent review paper by Strasberg and Winter published on PRX Quantum, in which they essentially formulate the first and second law of thermodynamics centered on the concepts of observational entropy. So they start from observational entropy and they build up a thermodynamic framework that starts from
so I'm wondering whether it's also might be useful in certain approaches towards explaining the emergence of classicality from
that would be
theory.
fantastic.
So for example, under coarse-grained measurements, people have shown that you get classical dynamics, for instance, and that seems to be quite natural in the context
Yes. Actually, it is born out of these insights, I think.
I see. Okay.
I mean, the occurrence of the word coarse graining is not by chance. It's because exactly people have in mind that.
Oh, very interesting.
Thank you.
Thanks for a very nice talk. Yeah,
Oh, yeah.
so I have two basic questions. So first one is, can we compute the asymptotic ID limit of this quantity of the observational entropy? Because like I'm asking this because like there is some kind
In
of
which sense?
optimization.
So this is defined like in this way, okay? So you should, there might be different ways in which, so let me go back to the definition. Yeah, it is defined in this way, right? So you mean, for example, you take row tensor n?
Yes, and then the doubt is like, what will we do about this P? Correct.
Yeah, but the P here is given, it's not optimized.
Ah, okay, it's a fixed thing.
Yes, it's a fixed thing. So you tell me, for example, you have a system of many particles and you say that this system, it can be a many-body system, but it has a state, rho. And then you tell me what kind of observations you can do on this system. That can be single partite or can be multi-partite. And so you give me P.
Okay,
And then I can compute this thing.
Okay, but if you take row tensor n, then the P that you'd apply to get these PIs, so then these will be P to the tensor n, is it?
No, I mean, it could be also, because these are defined independently, right?
Ah,
So
I
rho
see,
can
I
be
see.
tensor n, P can be non-tensor product form, or vice versa. P could be like just the tensor product of measurements, and rho might be instead a big global states of your system. So, you know,
I
the
see.
two things
Okay.
are.
Okay. And another thing is like, is there a generalization in some sense like omega key is relative entropy?
You mean like generalized divergences?
Yes.
Yes. That's actually something that we are considering at present, because if it's written in this way, you wouldn't know exactly how
Correct.
to do, no? Because you keep the volume like that, or
Yes,
you put
yes.
but once you write observational entropy as a relative entropy, then here, you know, you can play with statistical divergences and put any entropies, put whatever you like, and try to see what comes up out of there.
Okay. I see. Thank you.
Welcome.
Thank you very much for very beautiful framework of this observational entropy.
Thank you.
So this is related to also previous question, but so in the thermodynamics, if we think some isolated quantum system, it's microscopic von Neumann entropy is 0, but we have emergent thermodynamics,
Yes.
which looks like unique. So we can define some thermodynamic entropy and
Yes.
so on. And on the other hand, this observational entropy
Yes.
is really depends on the choice of PI used.
Yes.
So, but do you think in the end we get some kind of universality about?
Yes, because typically PI can be fixed to be the measurements that you can do in the laboratory, right? So it could be, for example, one macroscopic observable could be the center of gravity of your gas. Another macroscopic observable could be the average energy, the internal energy of the gas. So somehow, like the operational frame, your laboratory defines the P.
Yes, it.
Okay,
also,
and typically because laboratories are the same everywhere.
Yeah. But,
and then the P is almost the
what
same.
kind of quantity we really choose for PI? It is also maybe some flexibility.
Of course.
That's kind of universality.
So
as long as we coarse-grain quite.
So like when we do thermodynamics on a system, we have to decide first of all the degrees of freedom that you use to do thermodynamics on a system, right? For example, you can do thermodynamics with orthohydrogen and parahydrogen, just forgetting about the fact that there are two different gases, and you can do thermodynamics with it, or you could do thermodynamics by including also the state of the protons. No, so you have two different gases. So first of all, you decide the degrees of freedom that you do thermodynamics on. So you know there is a lot of arbitrariness. Like thermodynamics is not something that is there for everyone, just because we are typically interested in those quantities that are anyway hugely coarse-grained, and then the rest comes automatically. But there is a lot of freedom, yes.
So one more question is about this. So using your argument, so can we get some physical interpretation of Petz map? Some kind of
physical interpretation? No, I would say that this is really about inferential interpretation of Petz map. So Petz map is a kind of retrodiction. So you're sitting at the output end of a channel, of a communication channel. Communication, it can be whatever. So you're sitting somehow at the end of the process, and then you are trying to retrodict what was at the input. And to do retrodiction, you need a prior. So you need knowledge of the channel, of course, but you also need to assume a prior. That's why Petz map has that prior built in, because that's where, you know, Bayes' rule basically is hiding. In order to do Bayes reverse, you always need a prior, not to apply Bayes' theorem, which is, you know, the basic rule to do retrodiction. So it is, I would say that let's forget about physical meaning. Also, that's why I typically don't like to say, oh, I will do the time reverse evolution of the system, because we are not able to reverse time. We might try to engineer a Hamiltonian that has minus b instead of b, minus p instead of p, the x's instead are kept the same. You know, you can do all the tricks, but why we do that? Because then we wanted exponentiating that Hamiltonian forward in time. We actually get back u daga. So time always goes that way. And that's like, my point is that the second law does not solve one-wayness of time. The second law solves the one-wayness of inference. And then there is the problem of the cosmological arrow, which is a completely different problem. And I absolutely have no idea how to tackle this. But sometimes there are claims that, you know, there is the time arrow of the second law, and I would maintain the point that the second law has nothing to do with time, whatever that is.
Is there any question?
Can I ask a question?
Yeah, yes.
Can you hear me?
There is also Nakata-san. Okay.
Oh, yes. I'm Yoshi from online. I think you can hear me, right?
Yes, very well.
Okay, great. So my question is, well, first of all, thank you for a very interesting talk. So my question is about the like trace PI in the definition of observational entropy.
Yes.
And you know, in the definition, only trace appears, right? Trace PI, right? So meaning that so there are many different POVMs that result in the same value of observational entropy,
Yes.
right? My question is, but if you change the POVM, for example, then maybe, you know, the thermodynamics might be changed, right?
Yes. Yeah, sure.
So yeah, so my question is, you know, the thermodynamics might be changed by changing POVMs. On the other hand, you know, changing the POVM may not change this observational entropy. So I feel that there might be some gap between this observational entropy and thermodynamics. I may be, you know, missing something, but can you comment on that?
So as I said before, when you do thermodynamics, you have to tell me the thermodynamics of which degrees of freedom.
Sure.
So like everything starts from a laboratory.
Mhm.
So everything starts from the definition of some quantities that you can measure in your laboratory.
Mhm.
And so everything starts with a P.
Mhm.
Okay.
Yeah. And
So
in that sense,
is
you know,
the
my
sense
question
where-
is, you characterize the setting of the laboratory just
Yes.
by trace of PI. Right?
Yes, I define a laboratory as a P. You know,
PI is fine, but you know, in this definition of observational entropy,
yes.
you characterize it just by trace of PI.
Oh, these are just, yeah, this is the definition of yes, like this is what you get, but to do
So my
to
question
construct the
is,
coarse-grained state,
yeah,
the coarse-grained state
Mhm.
only depends on this PI. However, they are computed. For example, you could also do like a measurement just a very few times.
Mhm.
So you might say, okay, to get this PI exactly, you know, I
Oh,
need
sorry,
this many
not
statistics.
small PI, capital PI. So it's just, I mean, volume. What I'm talking about is a VI.
Yes.
And again, you know, my question is, this is just trace of capital PI.
Okay. Sorry,
Right.
this one. Yes.
Yeah, that one.
Yes.
But, you know, if you change the POVM,
Sure.
you know, we can choose many different POVMs that
Sure.
has the same value of VI.
VI, yes.
Yeah. So how can you kind of justify to characterize this thermodynamics by just a trace of capital PI? That's my question.
If it is a different POVM, we are looking at different quantities, physical quantities. So I don't see the problem. So different
I think
quantities
the
might be associated
thermodynamics
with different
changes.
VI.
Yeah. If
It's
you
like,
change
you
the
know,
P of,
if you imagine this VI to be the partition, the cells, the macroscopic cells in which you divide your phase space,
Mhm.
Then you might have a different division of this cell space, these
Right.
cells, right?
right.
That's exactly the same thing. So it amounts to a particular division of the initial Hilbert space into subspaces that are relevant for you.
Mhm.
But, you know, if you're interested in a different quantity, maybe, you know, you are looking at a different partition with different
Sure.
volumes of cells, and that's perfectly okay for me, at least.
Yeah, then, you know, the thermodynamics changes, but this observational entropy doesn't change. So that means,
But it would change for exist some rho, right? Or
yeah,
at least some state, it would change. Like if your P is different,
Mhm.
yeah, you might have two different rows and two different P's that give rise to the same number here.
yeah,
But, you know, thermodynamics is just one number. I mean, it also says dynamics in it, no?
Mhm.
So it's following some set of numbers in time, and these things would change.
yeah. So that means the you cannot describe the all of the thermodynamics, I mean, different thermodynamics by using this observational entropy.
So, well, first of all, I never said that the entire thermodynamics is done with this, right?
Okay, then that's fine. Okay.
Might be doable.
Yeah,
I
actually,
don't
I was
know,
just
okay?
interested in that question.
First, and then, sorry, what you said that I cannot do thermodynamics.
I mean, by changing
Like-
P of AMs, there are different thermodynamics. I think this is.
Nakada-san?
Oh yes,
Nakada-
changing the
sorry, maybe-
quantity.
Excuse me,
Yeah.
maybe time
Oh,
goes over.
Okay, yeah, sorry.
Okay,
Yeah.
sorry.
Yeah, anyway, thank you very much for a nice talk.
Thank you for the question. We will keep discussing on this
Yep.
surely later on. Thank
Okay,
you very
then,
much.
Let's thank the speaker again to close the section.
Thank you very much.